Okay. Mm, Good morning. Thank uh, Energy balance, steady state, open system, energy balance. Should refer to the books. It's in page 362. This is slide 2. In it. So, first class, we discuss about uh, closed system. So, for closed system, the equation is based on 7.3-4 using internal energy instead of heat enthalpy. So we have delta U plus delta EK plus delta EP equal to Q plus the divided 1 is for the closed system. So what does closed system mean? It's a system boundary. There are no mass can cross into or out of the boundary. Then we have open system. So vice versa. So for open system, the mass can cross the system boundary during the process. So the work will be done on the system to push the mass in. Work done on the surrounding by the mass that emerge from the system. So we have flow work and shaft work. So the work done on the system by its surrounding, we call it shaft work, or rate of work done on the process by moving part. So to move the mass into the system across the boundary, so you need something to push it. So in this case, that something to push it is done by, or this case is pump impeller. So the pump impeller is a shaft. So that's why they call it a shaft work. Next is the flow work. So flow work, since the system is open, so everything that comes in will come out. So the moment it come out, we call it flow work, WFL. In this case, WFL equal to V in, V in. So remember the dot is referred to the red. So we call that V in, V out here is the volumetric flow rate. P is measured. The specific properties and enthalpy. The properties of a process material are either extensive, proportional to the quantity of the material, or intensive, independent of the quantity. Example, measure number of mole, volume, mass flow rate, molar flow rate, volumetric flow rate, kinetic energy, potential energy, general energy, are all the extensive properties. For intensive property, it's temperature, pressure, density, or the scope. So meaning temperature, pressure, density, it is independent of the quantity. But for the extensive property, it is related to the quantity of the material. A specific property is an intensive quantity obtained by dividing an extensive property of its flow rate by the total amount of flow rate of the processed material. If the volume of the fluid is 200 centimeter cube, and the mass of the fluid is 200 grams, so the specific volume of the fluid is 1 centimeter cube per gram. We just divide. So that is the specific property. So what is it? So the intensive quantity obtained by dividing an extensive property, I think that relates to the quantity of the material. You divide it by the total amount of flow rate of the processed material. This is the example. Point number 2, if the mass flow rate of the stream is 100 kg per minute and the volumetric flow rate is 100 kg per minute, the specific volume of the stream material is 150 liters per minute equal to 1 times 100 kg per minute equal to 1.5 liters per kilogram. With the rate at which the stream transport energy is 200 joule per minute, then the specific kinetic energy. So the word specific for now it's over mass. It can be something else later. The specific kinetic energy of the steam tube is 300 joule per minute divided by 1,100 kg is 3 joule per kilogram. So if for the dot, it's referred to the rate. So this symbol is it like a head to denote the specific property. So this symbol will denote the specific value U head refer to specific internal energy. What is the specific? It's over, in this case, it's over weight. If the temperature and pressure of the processed material are such that the specific exceed the word specific internal energy, or meaning U is joule per kg, then a mass kg per second, that one is a regular, in this case mass flow rate of this material has a total internal energy of U equal to mu. A continuous stream of this material with the mass flow rate n transport internal energy at a rate U equal to okay. A continuous stream of this material with a mass flow rate n transport internal energy at a rate of U. You see U daughter of the rate of joule per second. This one to rate. This is the specific internal energy. Was the unit joule per kg. The property that occurs in the energy Lander equation for open system is Okay, is the specific enthalpy. So H refer to with the cap on top. That one refer to specific enthalpy. H is enthalpy equal to U, which is specific internal energy, plus P V cap. So refer to volumetric specific volume. Specific volume. Example, the specific internal energy of helium at 300 Kelvin and 180 N is 3,800 joule per mole, and the specific molar volume at the same temperature pressure is 24.63 liter per mole. Calculate the specific enthalpy of helium at this temperature and pressure at the rate at which the enthalpy is transported by a stream of helium at 300 Kelvin and 110 with a molar flow rate of 250 km per hour. So in this case, find the enthalpy H equal to U plus PV. To convert second term to joule, we need the factor joule per liter ATM from the gas constant table on the inside back cover. That one is available in hard copy books. So 0.008206. That one is this is the unit conversion. Dividing right hand side by the left hand side yield the desired factor. Therefore, okay, this is the unit conversion. So the unit must be similar, joule per mole, then we can add it up. So if N, this is a molar flow rate, it's 250 kilomole per hour. So the enthalpy rate of enthalpy is 1.57. So you must multiply. So H is equal to N, the molar flow rate, multiply with specific enthalpy. Then we get the enthalpy, rate of enthalpy, joule per hour. Exercise. Okay, you can do this exercise. The specific enthalpy. Specific internal energy of a fluid is 200 calorie per gram. What is the internal energy of 30 gram of this fluid? Jawab je lah. Okay, so 200 calorie per gram do multiply with 30 gram. When we get the U. So steady state open system energy balance. Tekan sikit kan. Okay. So first law thermodynamic for steady state open system is um, uh, first law thermodynamic equal to output. That one is done already. To signify the total rate of transfer of EKEPU by all process input stream plus the rate at which the G is transferred in as heat and work, and output is the total rate of energy transferred by the output stream. Can refer to equation 7.4-9. If EG, you refer to the total rate of energy transport by the G input or output stream of a system of or process, and Q and W again defined as the rate of flow of heat into and work on the process. So if M dot EQ dot PPG dot Q dot the flow rate of mass kinetic energy generated energy for the J process system, then the total rate at which the energy is converted to or out of the standard stream is U equal to M Uj plus Uj squared. So the first U is internal energy, second U is equal to the velocity. Divided by 2 plus GZ. Okay. So derivation. Total work done on the system equal the shaft work WS plus the flow work WFN. If Pj is the volumetric flow rate of the J stream and Pj is the pressure of the stream as it crosses the system boundary. So WFN so remember WFL refer to the when the fluid or the water goes out of the system boundary. So this is just discussion here is for the open system, meaning the mass can enter and out the system. So WFL refer to the mass it's exiting the process. WS, see the workshop is total work done to transport mass into the system. So W work equal to WS plus this equation, substituting the expression for EJ of equation 7.4 dash 10, and that for W work of equation 7.4 dash 11 into equation 7.4 dash 9. And bringing the PV term to the left side of the wheel, then we get 7.4-12. So 7.4 could be used for all steady state The system energy balance problem. As a rule, however, the term U plus PV is combined and written as hash cap G, variable previously defined as the specific enthalpy equal to mm, then use the symbol delta to denote the total output minus total input. So then, okay, delta. So in term of this quantity, question 7.4-13, and 4-13, the long one, this one, will become 7.4-15. So what is 7.4-15? Okay, so equation for open open system is delta H plus delta EK plus delta EP equals to Q plus W S. So question 7.4-15 that the net rate at which energy it, at which energy is transferred to the system as heat or shaft equals the difference between the rate at which the quantity P plus into energy plus potential energy is transported into and out of the system. So the H plus delta E plus delta EP. Notice that if a process has a single input stream and a single output stream, and there is no accumulation on mass of mass in the system, so that M in equal to M out into the expression for the H of equation 7.2 dash 14a simplify to delta H equal to, okay, this is delta H equal to M dot H out minus H. Okay, this is specific enthalpy of in. Okay. 500 kilogram per hour of steam drives a turbine. The steam enters the turbine at 44 atm and 450 degrees C at a linear speed 60 meters per second. Indicator 0.5 meter below the turbine inlet, there is no spill pressure and a velocity of 260 meters per second. To deliver shaft work at a rate of 70 kilowatts, and the heat loss from the turbine is estimated to be 10 to the power of 4 kilocalorie per hour. Oh, calculate the specific percentage change associated with the process. 500 going in and the going out 60 meters per second. That's 60 meters. 34 pm, 1 APM. What 70 kilowatt heat is 1000, 100,000 kilokalori. Okay, normally heat, work, and kinetic energy and energy. Some other determined energy per minute. Evaluate delta H, we will convert each term to kilowatt or kilojoule per second using conversion factors given on the inside front cover. First, noting that M equal to 100 kg per hour divided by 2,600. First, the M equal to 100 kg per hour divided by 2,600 second per hour. So we equal to 129 kg per second. Delta EQ here, 0.139 kg per second. We write with the unit conversion. This is outlet minus inlet and the velocity unit conversion. The delta EQ equal to 8.75 kilowatt. Delta EPMG. So in this case, this is 0.1, this is 0.3. Outlet 0.2, inlet 0.1. So M is 0.139 cubic second conversion. So it is gravity 0 minus I. So it's so delta EP to 6.1 10 of negative 3 kilowatt. Q, because we need to make sure the unit is same unit. See here, that's why they do this unit conversion to get kilowatt. Shaft work, yes, in kilowatt only. So delta H of enthalpy changes equal to this equation, the substituted inside can get negative 90 kilowatt. Besides, you can try this one. Mm, reference step is the properties. So reference step properties, let understand how to understand this to use the academic B. So it is not possible to know the absolute value of U, the specific energy or specific enthalpy for a process material, but you can determine the change in delta U or delta H corresponding to the specified change of state, temperature, pressure, and phase. Bringing a non-mass m of a substance through the specified change of state in such a way that all terms of the energy balance except delta U are known. So once delta U has been determined, delta H for the same change of state can use it as delta U equal plus delta PV bringing a non-mass m of a substance through the specified change of state in such a way that all terms of the energy balance except delta U are known or a convenient way to tabulate major changes in U or H is to choose a temperature, pressure, and state of application as a reference state. And to list delta U and delta H for changes from the state to a series of other states. Because later on, when we do energy balance, there are many things can happen, like changes in state of aggregation, meaning there are changes from liquid to, uh, vapor, a change in temperature only. For example, the temperature changes for carbon monoxide going from a reference state of 0 degrees C and 1 atm to two other states are measured with the following result. CO, so this one, gas, 0 degrees C, 1 atm to carbon monoxide CO. Yes, 100 degrees C, 1 atm, so delta H is 2919 joule per mole. How do we get 2919 joule per mole? Let us see. So next is changes in changes in temperature. So we increase the temperature to 500. The temperature is very high at 15,000 joule. So h cannot be known absolutely. For convenience, we will assign a value of h not equal to 0 to the reference state. Then h1 equal to h1 minus 0, equal to h1, h2, and so on. The table will be constructed for CO at 180 m like this. Note that the value 2919 joule for h at 100 degrees C does not mean the absolute value of the specific enthalpy at CO of CO at 100 degrees C is 2919. Because we cannot absolutely sure the value of the specific enthalpy, but yeah, so meaning we need to relate to the this 2919 is based on value based on the reference state of at 0 degree C, the enthalpy is 0. So we can say specific enthalpy at CO of carbon dioxide at 100 degree C and 100 m relative to CO at 0 degree C and 1 m is 2919 joule per minute. If two different tables are used, visual H1 and H2 are based on the same reference state. So delta H for CO going from 100 to 1200 degrees C at 1 m is 15,000 minus 2919. So we get 12,141 joule per mole if the reference state had been used to generate the specific enthalpy of CO at 100 degrees C at 100 degrees C. H1 and H2 would have different value, but H2 minus H1 would still be, yeah, it's true. Yeah. Regardless of the reference state, the value from 100 degrees to 500 degrees is always 12,141 joule per minute. This convenient result is a consequence of the fact that H like U is a state property or a property of a system from whose value depend only on the state of the system and not on how the system reached that state. Okay. Oh, this is example. The following entries are taken from a data table for saturated methyl chloride. What reference state was used to generate the given enthalpy? Mm. Liquid at negative 40 degrees. You see, because of the specific enthalpy is 0. Calculate the H delta U for the position of the saturated methyl chloride vapor from 50 to 0 degrees C. So for this case, 196. So calculate delta H and delta U for the transition of saturated methyl chloride vapor from 50 to 0. So 50 to 0, 9196, 23 minus 202. Yeah, yeah. Mm, You get negative 6.05 BTU per pound mass. What assumption? Okay, so next is this is for the specific enthalpy about specific internal energy. So you use this equation H equal to U plus PV. Assumption assume independent of P. This is what you need to do. Try the exercise later. I post the quiz. Thank you.